Hello YouTube, and in this video we are about to see how to design Netflix-like streaming platforms during a system design interview. But before that, if you're new to our channel, a warm welcome to you guys. We are software engineers from one of the FAANG companies, and via this channel we bring the best tips and tricks for you guys to crack your next tech company interview. With that, let's get right into it. A small disclaimer before we move any further. As with any system design question, it is highly subjective on how one designs it in reality. We did the thorough research for this video, but it could still be a little bit different from what Netflix has in place. But nonetheless, we are tackling this problem from a system design interview perspective. So it should be good to take the learnings from this video and then supplement with your research as well. With that out of the way, let's see what we have for you in this video. We will approach Netflix design from a pure black box perspective. So we will start off by gathering some of the requirements for designing Netflix. Main thing we want to tackle here is how Netflix interacts with its content creators and viewers, how Netflix deals with the scale. To give you some rough estimates, Netflix is live in more than 200 countries and serves more than 1 billion hours of video content in a week. To put that in perspective, YouTube does about 1 billion hours of video every day. Also, these numbers are from 2017, so it might be a little different today. Then we will see the high-level component diagram and divide the entire architecture into two planes, control plane and data plane. Don't worry if you have never heard of these terms, we will cover that in the video. We will also go over the secret sauce of Netflix, which is CDNs, short for Content Distribution Network. But if you are only here for CDNs and see how CDNs work, you can watch our distributed caching video. We'll post a link here on the video or also in the description. In the end, from an interview point of view, we will also see how to improve our system or some of the potential optimizations that we can apply. Plus, we will also see how to do the capacity planning at such a large scale, what key indicators to consider and apply them. I hope you are as excited as we are, so let's get right in. Alright, as we have mentioned earlier, with any system design interview, before even drawing anything on the board, we start by writing down some of the requirements for our system. And these can be as fine-grained or coarse-grained, depends on how the interviewer wants it. But we have also seen that interviewers let candidates take command of this piece of the interview and allow how they want to tackle the problem. Since Netflix is a really huge system, we have to be careful to not get pigeonholed into one area, but also not to be too generic to not touch some of the important components of the system. Netflix has two sets of customers. First set is content creators, which are going to upload their content on the Netflix's platform. This could be Marvel Studios uploading Avengers Endgame in their latest edition to the Avengers saga. And the second set would be viewers who are ultimately going to watch those videos. And they could have varying degrees of screen sizes, internet speeds, so on and so forth. So we should be able to work around that constraint as well. Also, we should tackle one of the spatial requirements, which is how to show subtitles overlaid on the video. Since it enhances the video watching experience for all the Netflix users, also would impress interviewers to think out of the box. One more requirement we can have is that how users would be able to search for any video in the Netflix's huge catalog in shortest amount of time possible. Unfortunately, given the limited length of this video, we won't be able to cover the content personalization aspect of the system and also how the billing or subscription model works in the video. But if this is something you guys are really interested in, please let us know in the comment section. We can definitely make another video on this topic. So now, as we know what our system should look like at the end of the day, let's start by drawing a high-level component diagram. This will help us get a bird's eye view and also help us interact with the interviewer so that he or she can help us if we are not considering certain excruciating detail of the system while we are designing it. This is also a great opportunity not just for you but also for your interviewer to see that how you approach an ambiguous problem and collaboratively come to a solution or a common ground and craft a really good solution. So here we have a content publisher or content creator who is interacting with this microservice, which we can call content uploader service. We'll get into the detail of this in a little bit, but you can imagine this thing to be a combination of web servers running on some AWS EC2 or Azure Virtual Functions or something like that. And then for the cloud storage solutions, we can use something like AWS S3 or Azure Blob Storage. Then we have our viewers or users on the other end of the spectrum, who with their endless options for the clients, for example, Amazon Fire TV or Samsung Smart TV, Apple iPhone, Android smartphone, can watch videos on different screen sizes. So they will be interacting with a separate fleet, which we can call playback service and steering service. So also don't worry about like if you are not understanding these things, we'll get into the nitty-gritty details for these services in a little while. But as we have mentioned earlier, we have divided our entire system into two planes, control plane and data plane. So control plane is like the brain of any system. It regulates and facilitates tasks in the body and liaison between different autonomous pieces of the system. Control plane can be a little bit lax about their latency SLAs, which is short for service level agreements, and we in cloud company use that a lot while we are designing stuff. So they are not on the direct live path to the customer, so they can be a little bit lax about their latency SLAs. But on the other hand, data plane is on the direct path to the viewers or customers, and it cannot be lax about the latency or performance SLAs, and they need to be responding at the magnitude of some millisecond latency to provide a really good or smooth video consumption experience. We'll see both of these in the detail in a little while. And in the end, as we have mentioned earlier, we have CDNs, short for Content Distribution Networks, which is the backbone for Netflix's fast response for smooth video watching experience. The control plane places the content for rendering those pixels at a blazing fast speed. We cannot miss this during a Netflix system design interview, so please pay close attention to this section when you face this question in real life. So let's start with the control plane first. Exhibit A, sequence diagram for control plane for the content upload scenario. And we want to highly emphasize on the fact that please draw sequence diagrams since they help in communicating designs much easily. We have content creators here on the one end, which are uploading their raw video file, and this could be in the magnitudes of terabyte. The reason for that is that we are not using a lossy compression to store these video files. So better the quality, bigger the size going to be. After that, the next step is to segment the video file into chunks. And this is done to break out the huge raw video file into mini chunks of, let's say, 50 to 60 kilobytes. And then all those chunks will now be stored onto some sort of cloud storage solution. Fun fact for you guys, Netflix uses AWS S3 to store all these chunks in real life. Actually, 90% of their cloud solution is provided by AWS. So that's why they ended up using AWS S3 since 2007. Two reasons for that. It is cheaper. Cheaper than to create and run their own S3-like data store. And the reason number two is it is reliable since Amazon has already invested a ton of money to perfect their system for general public use. So once these chunks are stored in the data store, then we have to pass them through a transcoder. So according to Wikipedia, transcoding is the direct digital to digital conversion of one encoding to another, such as for movie data files or audio files. This is done to make sure that a chunk is always available for a specific screen size and a specific internet speed. And this is an important step in uploading the entire video, since Netflix can't predict how your internet speed and screen size will going to be, but it can be proactive about showing you the right quality based on these constraints by doing the groundwork beforehand. Just to give you guys a rough idea, for Stranger Things Season 2, it was upwards of 9,000 video, audio, and subtitle files with all possible permutation combination. So we do want to mention that there is a wide range of heuristics goes into chunking like adaptive buffering or popular key moments in the movies. So instead of having a static cookie cutter size of each chunk sizes in itself can vary from scene to scene for each movie. And this is something we have covered in a lot more detail in our blog. So please find the link in the description, and you can also see how the whole transcoding and video encoding process happens. Once all these chunks are created from the original raw video file, these again gets uploaded to a cloud storage, like as we mentioned, AWS S3 or Azure Blob Storage. And then their URLs would be stored in some database, for example, Amazon DynamoDB or Azure's Cosmos DB. And this is how their data model looks like. It is pretty basic. So if you want, you can pause the video to study it more closely. And now at this point, Content Uploader Service tells the video distributor to fan out these chunks onto the CDN host worldwide. So now would be a good time to talk about these CDNs. Netflix created its first CDN network back in 2007, but they soon realized it is too big to run and manage. So they started looking into third-party CDN providers like Akamai, Limelight, and AWS CloudFront, which was recently launched when Netflix was making this decision in 2007. So Netflix thought that instead of paying massive amounts of money to these third-party providers, they can create a hybrid solution where they won't end up maintaining these stacks of servers and also not be dependent on third parties. Hence, they came up with the concept of Open Connect. And what we mean by that is like Netflix created a fleet of Open Connect appliances, short for OCAs, that they hosted at the ISPs, short for Internet Service Providers and Internet Exchange Points. So instead of finding a new lease for a data center, they contacted these local ISPs and IXPs to place these boxes. This made a lot of sense to ISPs and IXPs as well, since they know that Netflix runs at a very huge scale. To give you an idea about their scale is that they take up about 37% of the entire internet traffic. So all those bits and bytes flowing freely on the internet straight from Netflix's cloud storage would put massive pressure on limited internet infrastructure. So it was a win-win for both Netflix and ISPs to host these OCAs in these locations for pre-caching purposes. Now every time an uploader uploads a new TV show or movie, after going through this entire process of video processing, those chunks get stored on these OCAs. Although we covered it in some detail here, but OCAs deserve another video of their own. There's a lot of network engineering involved, but we can't cover all of that in this video. So let us know down in the comment section if you guys want us to create another video for their design as well. In the end, let's peel one more layer down, which is how to store subtitles so that they can be shown later when users play the video. So we can use OpenTSDB, which is a time series database built on top of Cassandra. And in here, we can see the data model for how to store subtitle information. So in this blob of data, we can see that we have a start time and the end time for that subtitle, and then the actual body of the subtitle. And so we will have like thousands or even like hundreds of thousands of these tiny blobs for the entire length of the video. Fun fact for you guys, Rohit Puri from Netflix gave a really nice talk on Netflix Media Database in this video, which is pretty incredible because this is how the subtitles work in general on any media streaming platform. So please check that out as well. You can find link in the description. Now, once user hits the play button, we want to see that what really happens in the data plane. So let's move on to exploring more about the data plane at this point. So here we have client on one end of the entire sequence diagram, and we can see that as soon as the user hits that play button, an HTTP request hits this playback service, and which is a small load balancer fleet in front of the Netflix's data plane. It forwards the request to the next available authorization host, which authorizes if user or client can view particular movie or TV show based on a view rating, or if the movie is R-rated or PG-13 or something, then the subscription limitations or the geographic legality. Some of the reasons for like doing that authorizations we can have here. Once it is ascertained that the user can indeed watch the video or the content, the request is forwarded to a steering service host, which returns the CDN which is closest to and alive to the user's location. Once the CDN link is returned to the user's Netflix's video player, the video player sends a request to that particular CDN for streaming those chunk back to the user. And the chunk selection happens based on the internet speed and the user's desired screen resolution. So during this time while the user is watching the video, it would be good for Netflix to collect some of the metrics, so about your viewing experience. So that's how Netflix does it, by letting the client talk to this playback service and then publish some events about your playback experience, and then finally uploading them back to a back to a playback experience service which tracks that in some sort of database. Small fun fact here we want to plug. We all know that Netflix is pretty performant, but how does all of that happen? We learned that Netflix uses gRPC for communication between different microservices, which has an added advantage of bidirectional streaming and minimum operation coupling, and is a much leaner version of REST protocol. So if you're interested in learning more about that, please go to our website. We have covered that in a lot more detail. This brings us to our last requirement on the list, which is content lookup. By content lookup, we just mean that whenever a user is typing some keywords on the search box, we want to show the content related to that keyword. So whenever we ask how to perform keyword searches, the inner workings of Google and suffix tries come to my mind. So we can use AWS Elasticsearch for this particular use case, which precisely gives us the ability to do that only, where we can store all the keywords that are associated with the video title in Elasticsearch's data store. And so we can design our solution something like this. So first the user types some keywords in the search box. The Netflix client sends those keywords or search query to this content discovery service, which then creates a request to find all the video titles matching that particular keyword to the Elasticsearch instance. If Elasticsearch finds any video title related to the keyword in the search query, content discovery service makes another request to the data storage to fetch the metadata for that video. Otherwise, it calls a content similarity service, which finds the similar video titles to that set of keywords in the search query, but then finally content discovery service returns the information about those videos that are similar to the one which are put in the keywords in the search box. So this is pretty much about it, how you will do a content lookup for any streaming platform, be it YouTube or Netflix or anything. Which brings us to our last section to explore some of the optimization or potential bottlenecks that we can improve in our design. So as we can see that there is something we can do about this playback service, which is a little bit like synchronous in a manner to get all the metadata information. So let's get a little bit more deeper into that shortcoming or bottleneck that we have here. So we just opened this playback service a little bit more wider and then listing a lot of isolated functions that it performs to return the playback data in the end. So what we have here is that we can see that a user makes a request and then the request dispatcher just waits for the user's content to come back, and then behind the scene this playback data IO requests two other services to get the device information which the user is using to play the media, and also the customer information for that user, that which geography he is from and stuff like that. And in the end, based on these two parameters, we decide that what playback data to show to him based on these two criteria. So based on these two criteria, in the end, we show what play data to be sent back to the customer. This works perfectly fine if latency is not an issue, but that is not the case in the real life. So as we can see that there is a huge bottleneck here, and we should rather make this service asynchronous, by which we mean that instead of blocking the server's execution until it processes the entire request end to end, we can implement an event pool, which is used to run the worker threads, where we can request for customer information and device information for each user in an asynchronous manner, and apply some callbacks to act when the responses come back for both these microservices. As you can see in the code snippet that we are making the request for customer information and device information in the asynchronous manner, and then zipping up their results back together and then making another request to decide the playback data in the end. If you're interested in learning more about these extensions and optimizations, definitely visit our website techtextula.com, and you can find the link in the description for that. So now let's move to another important aspect of the design interview that the interviewer may ask, which is to calculate the number of servers that are required to run a particular microservices. This is really important because you definitely want to showcase that your design doesn't lack the practicality of how the system will run at the end of the day, because you need to plan for the infrastructure cost as well. So this decision is dependent on different requirements. For example, what's the use case for this fleet or for this playback microservices? And the operation, is it compute heavy or disk heavy or both? So let's take one example from our design. So let's say that how many number of hosts we would need to run this playback microservice. So this is dependent on the number of concurrent connections that a host can withstand and the amount of permitted average latency that we can be okay with. And in the end, we want to see like what's the number of playback requests per second are, based on like what's the traffic's gonna be in the end of the day. So here we can see the formula for this thing, which is directly proportional to the number of playback requests made per second and the latency, and also inversely proportional to the number of concurrent connections that a server can maintain. So this would be, let's say that we have 75 million users at the peak time using the service, and all of them are expecting to have 20 millisecond of latency for their request. And we can only open up, let's say 10,000 concurrent connections to serve those 75 million requests. So at the end of the day, we would need like 150 servers which can open up these 10,000 concurrent connections simultaneously to maintain the playback microservice fleet. And this is a little bit high, on the higher end, because like it's really hard for a server to maintain cleanly 10,000 connections. So really we have to define a lot more engineering to cater that requirement. Fun fact for you guys, WhatsApp can open up actually more than 1 million concurrent connections on their Erlang based servers to handle these message traffic. This is something we covered in our WhatsApp system design interview video also. So follow the link in the description to check that out. Really interesting video. Don't want to miss that out. With that, we would like to end this video. We learned quite a bit about the Netflix ever so complex system. But at the end of the day, it comes all down to selecting the right set of tools and balancing the right trade-offs. Let us know in the comments if we missed anything or we should cover something in little more details. We'll definitely try to cover that in our future videos. Also, please subscribe to our channel. We have plenty of other videos on our channel that covers system design problems in depth. You can check that out in our playlist here. Also, if you like this video, click the like button and leave us a comment if you missed anything in the video. Your suggestions are always welcome. Also, if you want an in-depth explanation of this video, please head over to our website www.techtextula.com. Link is in the description. There you can play around with different brain exercises to fine-tune your knowledge about these topics. And as always, thanks for watching. Stay tuned. How to Design Uber is coming up next.